Great. Thanks, and sorry about those technical difficulties. I'm going to be discussing different data storage standards. Just as by means of outline, I'm going to go through different types of person-level clinical data and then different methods for storing data. Then I'm going to go through two widely used data storage standards within the clinical data space, as well as some of the standards that my team has implemented in a health information exchange in South Africa. I'm going to close off by discussing some trusted research environments, and then finally provide an index card of key considerations for data storage and usability. So to start off with the different types of health data, as I said, I'm going to be focusing on person-level clinical data, as this is what I focus on mostly. So we have patient identifiers and demographics, which can all be linked to a wide variety of different clinical data domains. And these clinical data domains can in turn be linked to providers, service areas, and terminologies or core concepts, which I think we've looked at in some of the previous sessions on curation. Now, just to break down those clinical data domains, they can typically be divided into some core data structures, and those are visits, referrals and appointments, laboratory tests for things like viral load tests or HbA1c results, etc., pharmacy data like drug dispensing data or prescriptions, radiology or other kinds of image data, which can be stored both as images or with, or usually in addition to images with metadata associated with those images, clinical notes and discharge summaries, which are typically stored as free text, diagnosis and procedure coding data, and then observations, which can really be a catch-all for many different things. Observations can range from biometric observations to things like weight and height, and observations of a patient's past medical history, like any previous adverse birth outcomes, etc. So all of these different clinical data domains are quite important to keep in mind when determining how you're going to structure your data. So this brings me to the different methods for storing data. We have relational or SQL databases. SQL is pronounced SQL. And then we have NoSQL databases, or not only SQL. So SQL stands for Structured Query Language. And in a SQL database, it's a relational structure whereby data are stored in different tables that can be linked to each other based on something. So in keeping in the line of person-level clinical data, typically different tables can be linked to each other by using the same person identifier. Within relational databases, we employ something called normalization, whereby we try and reduce duplication of data. So instead of storing the medication name on every line of medication data, we might just store a code and have a name in a lookup table. And relational databases have inherent constraints to prevent duplication and maintain these relationships. It makes it easy to query for very complex results. You can quite easily compare people's lab data and drug data all in one query. And you can use indexes to speed up queries. There's many different kinds of database servers as well for SQL databases. And most of these are open source or have community editions like MySQL, SQLite, Microsoft SQL, PostgreSQL, and MariaDB. Then we have not only SQL or NoSQL databases, and there we have different types. We get key value data stores, we get graph data, whereby you have different data points stored as nodes, and the relationships are edges between them. And then we get document stores. And these NoSQL databases are becoming increasingly popular because they allow unstructured data. They can be very dynamic, and they're particularly good for applications. So if you're developing like a mobile application in a clinical setting where there's multiple reads and writes, sometimes storing your data in a NoSQL format is the most efficient. But when it comes to analysis, it can require a lot more cleaning. And it can be a bit more difficult or reliant on some sort of a SQL-like language in order to query the complex results. And for NoSQL, there's also various database servers. There's MongoDB, which is freely available. I think CouchDB has a cost associated with it. And then there's Neo4j, which is a graph database. Then to just look at some different kinds of data storage standards for, I'll look at one for NoSQL and one for SQL. So for NoSQL, I'm going to be looking at a document storage standard, which is also used as a data exchange standard, and that is FHIR. FHIR stands for Fast Healthcare Interoperability Resource. And it's an HL7 standard, which means it's a standard really for exchanging data between applications. And we use it quite extensively for sharing data between our applications. FHIR documents follow what's known as a JSON or XML type structure, and I'll show an example of that in a minute. But what's really great about FHIR is it's a really well documented standard. It's got a great community of practice, and what they do is they divide different kinds of clinical data into different resources. So they have resources that kind of align with those clinical data types that we looked at in the very first slide, like a patient resource, an observation resource, etc. And these resources can all be bundled into one big document, which works really well for sharing and querying individual patients' data. The data typically needs to be transformed for analyses of multiple patients. Another advantage of FHIR is it's really well integrated with different terminology services and common concept methods. So this is an example of what a FHIR document looks like. I've put links as well. And this is what's called a bundle because it contains multiple resources. And one of the resources contained is a diagnostic report. And in that diagnostic report, we can see from the FHIR data that it was a lab test that was requested. And we can see which specific test with the SNOMED or common concept code, which is a blood culture for bacteria. And you can see what the patient details were, the provider, the result of the test, bacteremia due to staphylococcus. And then on the right, you can see a second resource, which is for a service request or an encounter, which just gives a little bit more detail about that visit that the patient had. So you can see from this document that it really is a great way to capture an individual patient, but to do some analysis on multiple patients does require some work. So now I'm going to discuss a relational database standard, which is called OMOP. So OMOP is maintained by the Observational Health Data Sciences and Informatics Institute, and they've developed a common data model called the Observational Medical Outcomes Partnership. And this really acts as a standard for data storage. It's incredibly well documented. It's open source. It's all on GitHub. You can go there and you can grab the code to generate tables in your database of choice, or if it doesn't have the format for your specific database, SQL database language, you can just tweak it quite easily. It relies on a common format as well as common formats for terminologies and vocabularies. And they've got really well documented methods for ETLs, so to bring CSV data or tabbed and limited data or any other kind of data into their data structures. So the way it kind of works is you can have multiple sources, which each have their own format. For instance, you might have data that's been collected in a REDCap database, or you might have data that's been received from healthcare providers in your area, and maybe some data from a laboratory system. And you can transform each of those different data sources into the OMOP common data model, and then you can harmonize the three, or you could even apply analysis methods to three different data centers with the same model and compare the results. So this is a person-centric model, as indicated in this diagram at the bottom right. And so every structure in this model is linked to the person table. And most of the other kind of structures can be linked to a visit. So you can link the drug exposures and the measurements, etc., all to a visit that has occurred. And using this structure, it can be really easy to identify cohorts with particular healthcare interventions and outcomes. So you could find all patients who received a particular lab test result that also received medication or perhaps didn't receive medication. You can also use it to predict occurrence of outcomes and estimate the effects that interventions can have in populations. So just to kind of highlight a couple of these design principles that they've implemented, they've really organized the data in a way that's optimal for analysis, and they've created a structure, especially with their GitHub account, whereby you can share your code for analyzing data in the OMOP format. By means of data protection, they've really limited what identifiable data should be captured into their structure. So it really is for analysis purposes as opposed to operational purposes. They've implemented standardized vocabularies, such as SNOMED codes, and that's really important when you want your system to be able to talk to other systems. And what's really great is it's neutral with regards to technology. Any relational database can be used, and it's quite scalable, and they've made sure that their model is backwards compatible. So this is an example of what data might look like in a OMOP structure. So this is showing, one line per column. Typically, you would have tables with multiple rows, but this just shows you how one patient's data might end up in this model. So I've got the person table on the left and the visit occurrence table on the right. And one of the really great things about this model is within each structure, it contains the source value as well as the mapped value. So if we look at gender, at the very bottom, there's a gender source value with F, standing for female, and then they've got the gender concept ID, which is the kind of cleaned up data in the OMOP format, and that concept ID in their concept dictionary refers to the female gender. And similarly, this can be used for other kinds of terms. So you'll see here on the right with their visit table, there's the visit source value is inpatient, and this maps to the visit concept ID of 9201 for inpatient admissions. It also just has kind of very logical structure with person, date, location if available, and provider if available in each table. Similarly, this is the condition table, and here you can see the condition coded by SNOMED code and when it was recorded first, and then the drug exposures on a given date. So as you can see from this structure, the OMOP structure is quite flexible. It covers almost every clinical domain that you could think of, and anything that isn't covered in one of the domain tables can typically be covered in the observation structure, whereby you can store your data in an element attribute value format. So now I'm going to move on to an example.
Sorry, Alexa, there's a question from Musa before we lose track of it.
Sorry, a question. Yeah, go ahead. Sorry, I can't see the questions. Thanks.
Oh, I think he's asking, saying that it was late, the meeting, what database you use. Not sure exactly what section or which slide. Musa, are you able to elaborate or explain the question?
Maybe just to say that OMOP can use any SQL database, so it's agnostic. So any relational database can implement the OMOP structure. So they've made sure that every field has a generic data type that is can be used across the different SQL languages, and that's all well documented in their model. Hope that answers the question. So now just to provide an example of a structure that's actually quite similar to OMOP. So I work in an environment called the Western Cape Provincial Health Data Centre, and essentially we're a very big data harmonization initiative, but with mostly an operational focus, and research extracts are just kind of a bonus of the operational data store. But we combine data from over 30 different routine sources of healthcare information on a daily basis, and store over 20 years of data for more than 14 million unique different patients. It's very highly sensitive data that we can use and do use for direct patient management, operational research, public facing dashboards, and academic research. And our structure is a relational structure that's really quite similar to OMOP, whereby we have a clinical database and a patient database. And I'm just going to quickly show that to you. I've hidden this slide, apologies. Yeah, so we have a relational database. Ours is in Microsoft SQL Server because that's what's available to us, but it can be implemented in other languages. We import data from various sources into a staging area where we do mapping and curation, and then we store our data in a clinical and patient database. And our clinical database, like OMOP, is structured into various clinical domains, like lab, pharmacy, etc. So I wanted to just reflect on some of the lessons that we've learned, because I think those are useful for other people setting up either big data harmonization initiatives, especially when it comes to person-level clinical data. And one of the most important decisions we made in the beginning, which came from, I guess, a combination of logic and also what's been done in other data centers in the world, is to separate patient and clinical data physically. So they're in two different databases, not just in two different tables. Depending on resource constraints, you might not be able to do that. But by separating the data, we can limit who has access to which kinds of data. We can particularly encrypt and mask the patient data, so that even if people have access to the patient data structures, like the births table or the deaths table, they might not be able to see who those records belong to. They could just see maybe the dates of death. We also, like OMOP, make sure to retain the raw and processed data, and that's been quite an important thing that we've done. So, for instance, with drugs, we receive drug data as recorded in the facility, and that might say one thing in their drug description, but actually it maps to a different kind of a drug code. And making sure that we have the raw data allows us to go back and interrogate how we've mapped and cleaned the data. Storing mapping and lookup tables has been a really big benefit to us. So of course, you want to make sure you use standard concepts and store those in lookup tables, but retaining how you've mapped your data, not just in code, but in some kind of a table structure that can be used for further curation, as well as to map new sources, has been really beneficial. Another thing that we've managed to consider is server security. That's been really, really important. We're lucky to be in an environment where that's managed for us, but things that are key to consider there are making sure that you have firewalls in place, that your access is limited. The people have to maybe access the environment via some sort of a secure VPN or on the actual network where the data lives. We've also had to make sure that our data is auditable and traceable. So we've got date stamps and things like that. So when you go back and you want to look at old research analyses, you can kind of see where the data would have come from. And then finally, and most importantly, documentation. So because I don't think OMOP probably existed when we started this, or it was in its early stages, we didn't have the values of the benefits of a pre-documented common data model. So we made sure to document our model quite carefully, and it's not perfect. It's a living process, but yeah, documentation of every field, of every table is extremely important when you start these kinds of projects with data harmonization, so that when new people come on, they can quite easily adapt to the environment. Then in terms of data sets for research, so because we have this huge operational data store, the benefit of that is for operational, the benefit for operational researchers and academic researchers is quite apparent, even though our primary focus is patient care. So we make sure, of course, that our researchers have ethical clearance, but when it comes to releasing data sets, we follow some key principles which I think are applicable to whether it's a data set that you've generated or one that you're sharing. Firstly, it's data minimization. We always need to limit data sets to exactly what is needed, and if possible, only share aggregated results. Because when it comes to clinical data, it's really, really hard to de-identify it. Most people, when they refer to de-identification, what they really mean is pseudonymization, which is really just removing the patient identifiers, and that's not enough. With enough access, you can quite easily figure out who a patient is just based on how many times they gave birth, or what their exact lab result was on a given day, because very few people will have the same observations. So, of course, separate your patient and clinical data, but take it a step further. Make sure that things are encrypted and password protected, even when you're working with them. If you can, employ data perturbations. So we've got a kind of a checklist that we use, and we make these as extensive as possible to minimize re-identification. Examples of those would be, instead of sharing a service area, we might share at like a facility level or at a street level somebody's address. We'd rather share the suburb or a district level information. Instead of sharing exact dates, we might just share the date and month. And instead of sharing exact values for lab results, we would share a category. So you don't see the exact value to a decimal point, you'd see a category. So this brings me to something that's recently been implemented in the UK by the NHS, and that is called a trusted research environment. And I think it's something that we could all actually employ in our own small research groups and larger ones. And this is where everybody works on the same shared secure platform. Now, the NHS has actually developed a platform called Open Safely, and the code behind that, as far as I understand, is completely open source. So it could be used and adapted to your own data. It doesn't need to, depend on the data that they provide. But what this does is it provides a standard environment where people can share code and working practices. And this relies, of course, on having very strong documentation and using a common data model like OMOP in this environment is helpful because the documentation is already done and online. But what it really does is if you get access, which of course will require your ethical clearance and those kinds of things, you get provided with a dummy data environment. And that dummy data environment allows you to test your code and work offline with data that resembles the raw data but is not the same. And then you can run your code and run and test your code on Open Safely in the environment and just extract your final results. This means that the raw data and large perturbed data sets never actually have to be released. And all the code that you execute against patient data can then be shared, and it's available in a public log. So the public can log on and they can see how many people have tried to access different kinds of data, what analyses have they been doing. And it's a really great idea, and I would encourage it for anyone working in a research environment that includes harmonized data. So finally, just some key considerations for data storage and usability. Firstly, do we have a secure environment where we can store and analyze the data that needs to be accessed? Second, does our team have the right skills, tools, and resources to curate, interrogate, and understand the raw data? And I can't highlight this enough. When it comes to data harmonization, it's not as simple as I'm sure you've learned over the past day and in your careers. It's not as simple as just getting data from one source and plugging it together with another. You really have to understand the source data, not just the structure. What does the data mean? You need to really engage with if it is clinical data, with the meaning behind that, if you want to be able to understand it and see patterns. Then what standard concept dictionaries can we use? Those are really important when it comes to harmonizing data. Can we use a common data model? And if we can't, how will we document what we do use? And then what measures will we put in place for patient protection? And lastly, will the data that we collect, generate, or harmonize in our initiative be available to others? And I think that's also quite important. With a lot of clinical research, people come and they request data, or they even go into facilities to collect data or disrupt the services in some way to be able to collect this data, which is beneficial for the public good, but often the results don't come back to the ground. And where possible, we need to feedback all of our information and make sure that the people who collected it for us are empowered to use that data in some way. And so just to close, I've listed some of those resources, links which we'll provide in these slides. I've got the OMOP data model, FIRE, and just sorry to say within the OMOP model, besides everything being available on GitHub, they also have some examples in like a kind of a textbook of their model, which you can run in some exercises, which can be quite helpful. Also included the South African Health Normative Standards Framework, just as some idea of how things can be standardized both for interoperability and data storage. A link to the Goldacre review, which is a really helpful review that reflects on harmonized data and trusted research environments. And then finally, a link to a set of papers on data center profiles from around the world, including the one that I mentioned, the Western Cape Provincial Health Data Center. Thank you. Any questions? I'm going to stop sharing my screen.
Thank you, Alexa. I think we have two questions in the chat. And thanks again for bringing this very clinical perspective in this workshop for your experience. I also have some few questions, but first let's the others go first.
Okay. I'll start with the first one. So can you elaborate on the separation of clinical versus patient data? Yes. So what we do is our patient's data is all kind of identifiable or demographic data, like kind of typically identifiable. So things like names, surnames, addresses, ID numbers, I don't know, health folder numbers, dates of death, dates of birth, gender, sex, religion, anything else that might be used as kind of a demographic identifier or direct identifier of a patient. So we make sure that all of that's in one database. Of course, in a lot of research environments, you don't have all that information, but you typically have, at the very least, date or year of birth and gender. And it is helpful even for that to be separate from the rest of your clinical data when you're analyzing it, because it will help prevent some of the risks of re-identification. And then the clinical data will include, all the other kinds of data, the lab data, pharmacy data, etc. Then how do you share access to your data for analysis, database, or API, or others? So when it comes to analysis, our particular data, we typically share to researchers with various files, and that's something we want to move away from because these files do get very big, but we do apply, as I said, all those data perturbation methods and security standards, and we have logging of all patients whose data were sent out to various users, and they're not allowed to see identifiers unless they have informed consent. And as far as possible, we also only release aggregated data. So usually via files. We do also have APIs, which our applications speak to. So we have patient-facing applications. No, we're building a patient-facing application, but we have a clinician-facing application rather that accesses patient data and through an API. Then with OMOP and FHIR, are they competing models or do they complement each other? Completely complementary. They do not need to be competing at all. I also agree that FHIR is more of a data transfer model and OMOP a data storage model, but people do also store data in kind of a FHIR compliant way or in some kind of a NoSQL database that can easily be transferred into FHIR. And the last question, I have a master student looking into FHIR. May I please have your email address? Sure, I'll put that in the chat. Thank you so much. Oh, yeah. How do you handle patients' data privacy for developers and database administrators having full access to the system? So this is a very tricky one. And what we do here is we limit the number of people who have access entirely. So there are very few administrators, and those administrators have to sign very extensive agreements as to what they're allowed to do with their access. We have an audit log which audits every single query that is run on our databases, so that if there was ever an issue, we could identify who was the culprit. And I think that's mostly the way we do that. But as I said, we try and limit who has full access to the system. Thank you.